We're in the same section 11.4, and we're talking about area. So in the past, we've talked about area of like functions. We have had something like this, and let's say that we had this function right there that we called f of x, and we said, okay, think about it as, we started with these rectangular approximations where if you're going from A to B, right, it might be like, okay, if we think about these as like little rectangles, so we divide this up into a whole bunch of different, sub-intervals within this interval. And then for each one, we either go up on the left-hand side or the right-hand side or the midpoint, or even if we use the trapezoidal approximations, so it's trapezoids instead of rectangles, we have a way to break it up into smaller things that we can actually evaluate, right? The area of. And then you add infinitely many of those together on this finite interval, and that gives us the exact area. Here, because we're dealing with the integral with respect to x, x increases, so we're moving from left to right and adding them all up that way, right? And then that gives us this terrible depiction of what it is, but all of those, and we add up all those, and that's a good approximation. Then all of a sudden we say take the limit as the number of those rectangles approaches infinity, and that gives us the exact area, right? That's the whole idea of the formal definition of the definite integral. Now, the variable that we're taking everything with respect to was x, so x increases moving from left to right. But now we're going to be talking about taking the integral with respect to theta. So theta sweeps through, and that's the whole thing, is it's this understanding of you're not just moving this way now, but it's sweeping through. And that's what you have to get in your head for this. So I'll show you what we are doing here. If we have some curve, and let's just, to make it easy, I'm going to say that it starts there and it does this thing. And we want to go from theta 1 all the way through to theta 2. Okay, so this is my whatever initial theta value, and this thing is sweeping through until it gets to theta 2. Now, some people might say, but theta 2 is less than theta 1 because it's to the left. No, theta is sweeping through this way, and so theta 1 is the lesser of the two angles in radians, and theta 2 is the greater angle. Do y'all see that? Okay, so we're sweeping through. Now, to really get to what's happening here, you could talk about sectors. So this is interesting because I was just talking about sectors today in aerospace engineering because we're talking about Kepler's second law and how it's talking about orbits, elliptical orbits and all that stuff. But so a sector is like part of a circle. Do you remember that? So if you were to cut up a piece of pie and you're able to locate the exact center of that pie, and you cut out a straight line from the center out to the edge, and then you could, whatever angle you decide, you then go there and then do another one, and then you have a slice of pie. And you could calculate let's take it two-dimensional at first, the area of that slice is known as a sector, so you're finding the area of that sector. So a sector is like a slice of a circle, right? So now, if we were to divide this up into, let's call it 3 equally spaced subintervals of theta, then it might be something like this. So that that angle is exactly equal to that angle, which is exactly equal to that angle. And let's say that we were basing the radius of each sector on the lower of the angle values. So then, I'll try my darndest here. Do you see how I would have from there, if I use the same r for this entire delta theta, or change in my theta values from there to there, I use my same r, that is going to be a sector. And here, the r value was pretty small, but I use that same r value here. So that's the radius of that sector right there. And there I'm using that r value for that whole subinterval. Do you all see what I'm doing? And then I could calculate the area of this sector plus the area of that sector plus the area of that sector and add them up, and that would be an okay approximation of the area for this entire thing. But then you could say, well, you could get a better approximation by doing what? More sectors, or sorry, more subintervals, or what that does is make a smaller delta theta, right? If your theta value isn't as large between the subintervals, right, the change in your theta values wasn't as large, then you would have more of those lines in there, and then you could, and that's the whole thing. If you were to apply the limit as the number of sectors approached infinity, then you're going to get what the formula is. So really quickly, do you remember what the area of a sector is? Yeah, in geometry you did. So it's going to be 1/2 r squared times theta. 1/2 r squared. So the area of a sector is 1/2 r squared times theta. So if theta was 2 pi, meaning that you went around the whole circle, then this would be 1/2 times the radius squared times 2 pi. The 1/2 and the 2 cancel out, and you're left with pi r squared. Does that make sense? If your theta value was just pi, that means that you're going around exactly half of the whole circle. And so the area is going to be 1/2 r squared times pi, or 1/2 pi r squared, which is half of the area of the circle. So this is the area of a sector. So we're not surprised to now get this formula that I'm going to give you, which is the area and I feel like I've done an adequate job of showing you where this comes from. I'm not going to get into it anymore because I feel like I've given you enough to see where this comes from. But area in polar coordinates. So if f of theta is a continuous, they call it function, right? But really that's the r equals f of theta. So r is equal to that f of theta. Then you're going from theta equals alpha to theta equals beta. Then the area of the region enclosed by the polar curve is just 1/2 times the integral from alpha to beta of r squared d theta. Bam.